Welcome to Study Session 9, Database Systems 2. Introduction. Databases are an important part of computer systems for storing persistent data. In this study session, you will be learning how to efficiently protect data and the design of systems that protect data. Learning outcomes. At the end of this study session, you will be able to 1. Explain data protection. Describe the architecture of database systems. Data protection. Databases can be a major investment. There are costs obviously associated with the hardware and authorized software such as a DBMS. Less obvious, perhaps, are costs of creating databases. Large and complex databases can require many man-years of analysis and design efforts involving specialist skills that may not be present in the authorized one. Thus, experienced consultants and other technical specialists may have to be brought in. Furthermore, in the long term, an authorized one must also develop internal capability to maintain the databases and deal with changing requirements. This usually means hiring and retaining a group of technical specialists, such as DBAs, who need to be trained and retrained to keep up with the technology. End users too will need to be trained to use the system properly. In all, databases can be very expensive. Aside from the expenses above, databases often are crucial to a business. Imagine what would happen, say if databases of customer accounts maintained by a bank were accidentally or maliciously destroyed. Because of this actual and potential cost, databases must be deliberately protected against any conceivable harm. Generally, there are three types of security that must be put in place. 1. Physical protection. These are protective measures to guard against natural disasters, for example, fire, floods, earthquakes, and so on and so forth. Theft, accidental damage to equipment and other threats that can cause the physical loss of data. This is generally the area of physical installation management and is outside the scope of this book. Operational protection. These are measures to authorize or even eliminate the impact of human errors on the database's integrity. Errors can occur, for example, in assigning values to attributes. A value may be unreasonable, for example, an age of 213, or of the wrong type, e.g., the value Smith assigned to the age attribute. These measures are typically embodied in a set of integrity constraints, a set of assertions that must be enforced. That is, the truth of the assertions must be preserved across all database transactions. An example of an assertion might be the price of a product must be a positive number. Any operation then is invalid if it violates a stated constraint, e.g., store_price equals minus 9.99. These constraints are typically specified by a DBA in the database schema. 3. Authorization protection. These are measures to ensure that access to the databases are by authorized users only, and then only for specific modes of access. E.g., some users may only be allowed to read, while others can modify database content. They are necessary to ensure that confidentiality and correctness of information is preserved. Access control can be applied at various levels in the system. At the installation level, access through computer terminals may be controlled using special access cards or passwords. At successively lower levels, control may be applied to an entire database, to its physical devices or parts thereof, or to its logical parts, part of the schema. In extremely sensitive problem domains, access control may even be applied to individual instances or data objects in the database. Architecture of database systems. Software systems generally have an architecture, that is, possessing of a structure, form, and organization function. The former describes identifiable components and how they relate to one another structurally. The latter describes how the functions of the various structural components interact to provide the overall functionality of the system as a whole. Since a database system is basically a software system, albeit complex. It too possesses an architecture. A typical architecture must define a particular configuration of an interaction between data, software modules, metadata, interfaces, and languages. The architecture of a database system determines its capability, reliability, effectiveness, and efficiency in meeting user requirements. But besides the visible functions seen through some data manipulation language, a good database architecture should provide A. Independence of data and programs, B. Ease of system design, C. Ease of programming, D. Powerful query facilities, E. Protection of data. The features listed above become especially important in large organizations where corporate data are held centrally. In such situations, no single user department has responsibility over, nor can they be expected to know about all of the organization's data. This becomes the job of a database administrator, DBA, who has a daunting range of responsibilities that include creating, expanding, protecting, and maintaining the integrity of all data while addressing the interests of different present and future user communities. To create a database, a DBA has to analyze and assess the data requirements of all users and from this determine its logical structure, that is, database schema. This, on the one hand, will need to be efficiently mapped onto a physical structure that optimizes retrieval performance and the use of storage. On the other, it would also have to be mapped to multiple user views suited to the respective user applications. For large databases, DBA functions will in fact require the full-time services of a team of many people. A good database architecture should have features that can significantly facilitate these activities. Data abstraction. To meet the requirements above, a more sophisticated architecture is in fact used, providing a number of levels of data abstraction or data definition. The database schema, also known as conceptual schema, mentioned above represents an information model at the logical level of data definition. At this level, we abstract our details like computer storage structures, their restrictions or their operational efficiencies. The view of a database as a collection of relations or tables, each with fixed attributes and primary keys ranging over given domains, is an example of a logical level of data definition. The details of efficiently organizing and storing objects of the conceptual schema in computers with particular hardware configurations are dealt with at the internal storage level of data definition. This level is also referred to as the internal schema. It maps the contents of the conceptual schema onto structures representing tuples, associated key organizations and indexes, etc., taking into account application characteristics and restrictions of a given computer system. That is, the DBA describes at this level how objects of the conceptual schema are actually organized in a computer. At a higher level of abstraction, objects from the conceptual schema are mapped onto views seen by end users of the database. Such views were also referred to as external schemas. An external schema presents only those aspects of the conceptual schema that are relevant to the particular application at hand, abstracting out all other details. Thus, depending on the requirements of the application, the view may be organized differently from that in the conceptual schema. E.g., some tables may be merged, attributes may be suppressed, etc. There may thus be many views created, one for each type of application. In contrast, there is only one conceptual and one internal schema. All views are derived from the same conceptual schema. This is illustrated in figure, which shows two different user views derived from the same conceptual schema. Thus, modern database systems support three levels of database abstraction: external schemas, user views, conceptual schema, and internal storage schema. The DDL is basically a tool only for conceptual schema definition. The DBA will therefore usually need special languages to handle the external and internal schema definitions. The internal schema definition, however, varies widely over different implementation platforms. That is, there are few common principles for such definition. We will therefore say little more about them in this book. As to external schema definitions, note that in the relational model, the data sublanguages can be used to both describe and manipulate data. This is because the expressions of a data sublanguage themselves denote relations. Thus, a collection of new derived relations can be defined as an external schema. For example, suppose the following relations are defined. Customer for C, name, city, phone, P for product and price, T for transaction, C, P, date and quantity. We can then define an external view with a construct like the following. Define view my transaction 1 and select CNAME and select customer name, customer city, date, total sum, equal price, quantity from customer transaction product, where customer C hashtag equals transaction customer, transaction P equal product, which defines the relation view my transaction. Now, these definitions effectively maps the conceptual database structure into a form more convenient for a particular user or application. Functions of a DBA include creation of the database. To create a database, a DBA has to analyze and access the requirements of the users and from this determine its logical structure. In other words, the DBA has to design a conceptual schema and a first variant of an internal schema. When the internal schema is ready, the DBA must load the database with actual data, acting as intermediary between users and the database. A DBA is responsible for all user facilities determined by external schemas. That is, the DNA is responsible for defining all external schemas or user views, ensuring data privacy, integrity, and security. In analyzing user requirements, a DBA must determine who should have access to which data, subsequently arrange for appropriate privacy locks, passwords for identified individuals and all groups. The DBA must also determine integrity constraints and arrange for appropriate data validation to ensure that such constraints are never violated. Last but not least, the DBA must make arrangements for data to be regularly backed up and stored in a safe place as a measure against unrecoverable data losses for one reason or another. It may seem like a database can be developed using the conventional waterfall technique. That is, the development process is a sequence of stages, work progressing from one stage to the next, only when the preceding stage has been completed. For relational database development, this sequence will include stages like eliciting user requirements, analyzing data relationships, designing the conceptual schema, designing the internal schema, loading the database, defining user views and interfaces, through to the deployment of user facilities and database operations. In practice, however, when users start to work with the database, the initial requirements inevitably change for a number of reasons, including experience gained, a growing amount of data to be processed, and in this fast-changing world, changes in the nature of the business it supports. Thus, a database needs to evolve, learning from experience and allowing for changes in requirements. In particular, we may expect periodic changes to improve database performance as data usage patterns changes or becomes more clearer. Add more clients. Add new applications to meet processing requirements. Modify the conceptual schema as understanding of the enterprise's perception of data improves. Changing a database once the conceptual and internal schemas have been defined and data actually loaded, can be a major undertaking even for seemingly small conceptual changes. A good DBMS should therefore provide facilities to modify a database with a minimum of inconvenience. The desired facility can perhaps be broadly described to cover performance monitoring, data reorganization, database restructuring. By performance monitoring, we mean the collection of usage statistics and their analysis. Statistics necessary for performance optimization generally fall under two headings: static and dynamic statistics. The static statistics refer to the general state of the database and can be collected by special monitoring programs when the database is inactive. Examples of such data include the number of tuples per relation, the population of domains, and the distribution of relations over available storage space, and so on. The dynamic statistics refer to runtime characteristics and can be collected only when the database is running. Examples include frequency of access to and updating of each relation and domain, use of each type of data manipulation operator, and associated response times, frequency of these access for different usage types, and so on. It is the DBA's responsibility to analyze such data, interpret them, and when necessary, take steps to reorganize the storage schema to optimize performance. Reorganizing the storage schema also entails the subsequent physical reorganization of the data themselves. This is what we mean by database reorganization. The restructuring of the conceptual schema implies changing its content, such as adding or removing data items, that is, columns of a relation, adding or removing entire relations, splitting or recombining relations, changing a relation's primary keys, and so on. For example, assuming the relations as on page 2, suppose we now wish to record also for each purchase transaction the sales representative responsible for the sale. We will need therefore to add a column into the transaction relation, say with column name, transaction C, cost, price, R, date, and quantity. The intention, of course, is to record a unique value under this column to denote a particular sales representative. Details of such sales representatives will then be given in a new relation. A restructured conceptual schema will normally be followed by a database reorganization in the sense explained above. Data independence refers to the independence of one user view external schema with respect to others. A high degree of independence is desirable as it will allow a DBA to change one view to meet new requirements and/or to optimize performance without affecting other views. Relational databases with appropriate relational sublanguages have a higher degree of data independence. Data independence is also used to refer to the independence of user views relative to the conceptual schema. In general, if the relations and attributes referred to in a view definition are not removed in a restructuring, the view will not be affected. Thus, we will accommodate new additive requirements without affecting existing applications. Data independence. Lastly, data independence may also refer to the extent to which we may change the storage schema without affecting the conceptual or external schemas. We will not elaborate on this as we have pointed out earlier that the storage level is too diverse for meaningful treatment here. Study session summary. In this study session, you have learned that data protection is very important to databases, that a good database architecture should facilitate data abstraction, data administration, and data independence, that there are 3 types of data protection crucial to databases: physical protection, operational protection, and authorization protection. End of study session 9. Thanks for listening.